Hello everybody. I want to take an opportunity to solve this problem where we're asked to calculate the coefficient of variation. And I'll go into two levels of explanation on it. I'll tell you how it's done, how to use StatCrunch to help us out a little bit, and I'll tell you a little bit about why we approach this question the way that we do. Okay, so the formula is given, so there's no mystery about that. The coefficient of variation is the standard deviation over the mean times 100%, and we can just accept that for now if you want to. So in this data set, I have heights and weights for, I guess, I don't know if it's 12 of the same people or two groups of 12, but we have 12 measurements, 12 heights, 12 weights, right? Okay. Different types of measurements. A height and weight are different things, okay? Now, I can, if I want to, open this in StatCrunch, because in order to calculate the coefficient of variation for heights and weights, I need to find the standard deviation and the mean. And I can do that on paper with pencil. I can write out the calculations and use a handheld calculator if I want to, but I'll use StatCrunch, okay? So I'd open it in StatCrunch and it put the heights in one column and the weights in another. And then to calculate the mean and standard deviation for the heights and the weights, I can go to Stat, Summary Stat, and I choose columns because my heights and weights are two different things individually in columns. And then I could select heights or weights or do them both at the same time. And then I want the mean and the standard deviation. So I do something like this. Okay, and then I do compute, and it would give me these numbers. All right, so I appear to have what I need, all right, to do this. So let's do this now. Let's go over to my slides. Oops, hold on just a second. Oh. Okay. So here are the numbers that I got from StatCrunch right here. For the heights, the mean was about 71.25 inches. The heights are measured in inches. And the weights, mean was 199.333. So on pounds, for the heights, the standard deviation was about 5.25 inches, and for the weights, the standard deviation is 15.58 pounds, okay? Now, I keep saying pounds and inches because I want to emphasize heights and weights are different, and what I mean by that is we use different units of measurement to quantify them, okay? Now, the question that we're getting at when we calculate the coefficient of variation is which measurement is more variable? What do I mean by more variable? Which of these numbers are more spread out, okay? One thing we're interested in when we describe data is where the data is, which is roughly what the mean tells us. And then the second question is, well, how spread out is it? And that's what the standard deviation tells us, okay? So the question here is, which are the heights more spread out or are the weights more spread out? Okay, that's what we're answering. But height and weight are two different things. And just because the weights have a larger standard deviation, look, 15 is a bigger number than 5. But, a pound is a different sort of thing than an inch. Okay, so we're not comparing the same thing here. Okay, so, all right, if I was to try to tell you which of these numbers were more spread out, I can't tell you just based on this number being the larger standard deviation. Okay, it might be, but I can't say that just because this number is bigger. So here's how we go about it. We compared the dispersion, the variability, the spread of the data by the coefficient of variation. Here's that formula that was given with the question. It's fairly simple to calculate once we use StatCrunch to get the standard deviation and mean, and that's the way I'm doing it right now. I use StatCrunch, and for the heights, there's the standard deviation divided by the mean, and you multiply that by 100%, I get 7.381 0.32%. And for the weights, the coefficient of variation, here I take the standard deviation divided by the mean times 100%, I get 7.81981%. So it comes down to which of these numbers is bigger. 7.8% is bigger than 7.3%. So that means the weights are more variable. So look at how I answered this. I put in the coefficient of variation. Notice here it says round to the nearest tenth. So I took 7.38 and I rounded it to 7.4. But there's the coefficient of variation for the heights and the weights. Okay, those are just calculations. And then my conclusion was the weight was more variable because the coefficient of variation is bigger. Okay, so that's how we do it. That's how we answer the question. Now, in case you're interested, I understand not everybody's interested in this kind of thing, but why not take a deeper look? I'm already making the video, and you know, I think the deeper you understand something, the better if you're going to learn it. So I'll try to explain a little more about why we use the coefficient of variation. So, but let me also take this chance to review a little bit about something. We could say that it's a very, very safe bet that virtually all the data will be within 3 standard deviations of the mean. Okay, so let's compare like two made up samples. Okay, say we kind of did the same thing. We had one group of 12 people and we had another group of 12 people, and I measured their heights. Okay, and on the first group the mean was 70 inches and say the standard deviation was 5 inches. Now I'm saying virtually all the data, it's a safe bet, will be within 3 standard deviations of the mean. So here's a graph, a number line, showing me where the numbers are. Like, you know, if 70 is the mean, okay, and 3 standard deviations up, that would take me 15 inches up, that'd take me to 85, and 3 standard deviations down, that'd take me 15 down, that'd take me to 55. So, you know, these people here, okay, virtually all of their heights are somewhere between 55 and 85 inches. Okay, very safe bet. I can't, you know, we cannot guarantee that there's not somebody in the sample who's 52 inches tall or 87 inches tall, but you know, like I said, this is a safe bet. Now, say there's another group of 12 people, let's say, and they also have a mean height of 70 inches, but the standard deviation is only 2 inches. Okay. Well, that says that virtually all the data is, well, so 3 standard deviations above or below the mean. Standard deviation of 2 takes me 6 up and 6 down. So here I can tell you virtually all the data are somewhere between 64 and 76 inches. Okay, so they measured everybody's heights, right? It's a very safe bet that virtually all of their individual measurements are between 64 and 76 inches. Maybe somebody was 80 inches tall, who knows, right? Anyway, so, but what's the spread look like? I mean, here I got a 30-inch spread. Like I'm saying, like, you know, I don't know what the individual numbers are, but with our thinking that virtually all the data is between 3 standard deviations of the mean, then that's a 30-inch spread of where those numbers probably are. And here with this one, it's only 12. All right. So you see, like, if I'm comparing the same thing, it's easy to say that these data are more spread out. I mean, we're just comparing the same thing. There's like no magic to it at all. But when you're not comparing the same thing, when you're comparing measurements that are in inches and measurements that are in pounds, then, you know, it's like saying, it's like asking, what's more, 15 inches or 15 pounds? Well, they're not the same thing. You know, I can't tell you which is more. All right? So hopefully that deeper look will allow you to see why, when I'm trying to tell you here which data is more variable or spread out, I can't just say it's this one because the number's bigger. That number's in pounds, this number's in inches, and they're different things. Like, okay, as I hopefully have emphasized. So, well, okay, what's the coefficient of variation do? When we're comparing different things, we want to say which of 2 data sets is more variable or spread out or dispersed. The coefficient of variation describes the standard deviation as a percent of the mean. Okay, so it takes the units of measurement out of it. That's what it does for it. So you take the mean being whatever it is, The standard deviation is like a portion of the mean. And we could say between two different things, is it a bigger portion or a smaller portion? That's what I was doing when I calculated both of these and said, well, that's the bigger one. That means the weights are more dispersed and more spread out.